Thank you, Cameron. I'm Dylan. I've been with ERDIC for 14 years or so now. I've been working on this project for over a decade now. This is something that we've started with magnesium phosphate concrete, looking at it for airfield pavement applications, and we literally started this project with the popsicle stick and a cup and stirring the binder together in a cup and it getting stuck, and then taking it all the way to an application. Guess I need to stay close. Ooh. So this is an outline. It's a very wordy outline, but it's essentially going to go through a problem statement, intro to what magnesium phosphate concretes are, why they worked for our application, the objectives, and then the project itself, where we looked at the proprietary materials that are available. We developed our own material, and then we went through a field trial. We had setbacks from a field trial. We did another field trial. We had setbacks with that one too, and then we ultimately got everything resolved and then did an actual placement out at Cannon Air Force Base and out in New Mexico that's been in service for about 3 years now. So that's the arc of the story, and we'll get there. So the problem statement is aircraft, they're designed to fly. They're not designed to sit on the tarmac, and so when they're sitting on the tarmac, they're leaking oil, they're leaking petroleum, they're and leaking who knows what else. They also have exhaust coming out of them that's heat. That heat can also expedite the process. So the picture on the right, well, the parking apron that we did these placements at was for V-22 Osprey, so it's a tilt-rotor aircraft, so it takes off as a helicopter, then it flattens out and flies more like a traditional airplane. And then the picture on the right is some of the typical damage that you can see under these aircraft, under the two motors. So the motors are in the wings, the tilt-rotors, and that's what you see on either side of it. And I'll talk about how that happens here in just a bit. So the scaling of Portland cement concrete. So the areas exposed to the POLs, petroleum oil lubricants, and jet wash can see severe damage that expedites, the process of, the Air Force having to come in and replace it and do repairs. And even concrete designed to UFGS, the high heat UFGS, so the UFGS is the Tri-Services standards that we do airfield pavements on, and even the high heat version sees damage from these aircraft. So first step, we had to figure out what was going on. So we sent somebody out. He took thermal imaging while the aircraft was starting operations. We obtained damage samples, and then we did forensic analysis with SEM, EDS, and XRD, and a host of other forensic equipment that we have. And long story short is that the high pH of concrete is reacting with the POLs and forming phosphoric acid, and that phosphoric acid is attacking the binder of the concrete. And then so you get this iterative damage process, this scaling away the binder, then you get aggregates to pop out, and then you're exposing more binder, and it's just a layer by layer damage type thing that you're seeing. And so, and the heat only exacerbates that process. And so magnesium phosphate concrete, our inspiration for all this is these are commonly pothole fillers, is what I call them, because they're so rapid setting. You really can't work with them. And so most times they come in a 5-gallon bucket, pre-blended. You got your handheld mixer and you mix it and you're filling a pothole with it. You get high early strength gain, and it's used by a lot of DOTs because you can return the traffic in less than 4 hours. So Air Force personnel was using this proprietary MPCs as a patching material. And then after continued exposures, some of them noticed that the MPC repair was performing better than the OPC concrete around it, ordinary Portland cement concrete around it. And then so we got some operational feedback, and I apologize for all my animations. I went a little haywire. And then the Air Force contacted us. That's AFCAC, Air Force Civil Engineering Center. They contacted us, said, hey, we noticed something here. What's going on? How can we replicate this, and can we use it at scale? So that was the whole birth of this project, if you will. And so we went through and developed a project. Is first come up with the mixed design process for MPCs. At the time, it was 2014, we weren't aware of any mixed proportioning methods for MPCs. Everything was heavy in the literature. Of course, all the proprietary materials, nobody's going to tell you what's in their concrete, and so we had to sort of grassroots figure that out ourselves. Then we had to understand the exothermic acid-base reaction mechanism, control the setting time. It's very rapid setting. It's hard to place a parking apron if it's setting up in 20 minutes. So there's several ways you do that with MPCs. And then also the rest of it is sort of the constructability aspect, is you want to characterize, is develop joint spacing guidance. Can we do full depth repairs? Can we do partial depth repairs? When do we do doweling? All this other kind of stuff. And then the ultimate goal, which we're still working on, is eventually develop QA/QC guidelines for magnesium phosphate concretes, and then also develop, airfield construction specs. So we're getting there. So intro to the MPCs this is the binder portion of it, is magnesium oxide, phosphate salts. Those are your main two binder materials. That's what forms your acid-base reaction. And then you have a fly ash, and the fly ash helps with the reactivity, but its main purpose that it serves in this is slowing that reaction down without degrading strength. And then you also have water, and then you add it, and you add your aggregates, and you get concrete, and then also boric acid is the most common retarder used in MPCs, but there's some caveat with the boric acid that I'll get to in a bit. And then the whole point is, with UHPCs or whatever else, you want to drive the formation of CSH. So for magnesium phosphate concrete, you're trying to drive the formation of struvite K. And so I called it the CSH for MPCs, but its morphology is similar to ettringite, and then there's just the chemical process. You got your magnesium oxide, your potassium phosphate, which is actually a fertilizer, then you have water, and then there's your struvite K formula. So advantages, rapid setting, could also be a disadvantage, but high early age strength, bonds well to existing concrete, low drying shrinkage, acid resistance, chemical and mold resistance. It's got a low coefficient of thermal expansion and reduced CO2 emissions. Disadvantages, rapid setting. There is potential, it's a whole balancing act when you're designing these materials. The phosphates are highly, highly, highly water soluble. So if you have any unreacted phosphates in your system, if water gets into it, you can actually leach those phosphates out and leave voids, and you have porous concrete. And then it's highly exothermic. I mean, that's in a third of a 6x12, and we're at 170 degrees on the edge of it. And so it's also difficult for large placements. And then it's thixotropic, which thixotropic means that when you agitate it, it becomes more flowable. And then when you stop agitation, it starts to solidify, but not necessarily set. And so, yeah, that one is fun. We were supposed to be doing time of set on them, but it didn't go well for us. So this is the proprietary material investigation. So we started out with 3 proprietary materials. We got a material from Premier Magnesia, Master Amaco, and then Pavement TR. And we took the 3, we tested them all at their designed, at design, and then we did it 20% above design, 20% below design, and then also with the boric acid, with water and with boric acid, and varied it. We did a whole host of testing, and the main takeaway here is that, this is your water content going up, compressive strength on the y-axis, but in the blue, red, gray, yellow is as you add boric acid, you're actually degrading strength. So it's sort of a balancing act that I'll talk more about, is that you have to have it because you need the working time to be able to do it in large-scale applications, but you're reducing your strengths when you add it. So it is definitely a balancing act in that sense. And so all of this work is documented in a ERDIC technical report. That's the citation for it. So look it up, and then I can talk more about it later as well. So the balancing act I was talking about, this is about mostly the paste right now. There's big things in the literature. You're going to see your magnesium to phosphate ratio. A lot of people give that to you in molar ratios. You can get it in mass ratios, however you want to do it. Your water to binder ratio is typically a 0.1 to 0.4. Most people are around a 0.2. Fly ash amount, you're upwards of 40, 50, 60% fly ash. You want a Class C, Class F. You typically want a Class C in these. Class C can help you drive the formation of more struvite. And then boric acid was our retarder type, increased set time, but then also that strength deduction that I showed on the last page. And then it's the whole balancing act between all those. So then with the concrete, you got aggregate type, you got your aggregate to binder ratio. These are sort of your normal concrete-y things. And then you also have your aggregate grading, which plays a role in your performance as well. So this is a dizzying slide, but this was our methodology as we go through. We're looking at it's the magnesium phosphate ratio. We varied it from 2:1 to 4:1, water binder ratio, retarder type, and then fly ash, what type of fly ash, how much fly ash. We also looked at the magnesium oxide. There's light burn, hard burn, and dead burn magnesium oxide, so which one of those performs the best for us. And then also there's the phosphates. There's sodium phosphates, potassium phosphates, ammonium phosphates. Well, we quickly decided to go with the potassium phosphates because the ammonium phosphates can actually release ammonium gas when they're done being mixed. And then we go through, we balanced a lot. And so we had inputs of kind of our factors in our design of experiments, if you will. Magnesium to phosphate ratio, and that's a molar ratio you see on the screen. Aggregate to binder ratio, fly ash, and then the properties studied, at least initially, were compressive strength of cubes, cylinders if we added coarse aggregates, and then time of set via the penetrometer. And so we started out, we did light burn, we did the hard burn, and we quickly learned that dead burn gave us the best strengths and also the best set times. So the burn is all associated with the temp at which it's calcined in a furnace. So dead burn, I believe, is 1200 C, maybe more than that. And so we varied them. We quickly settled on a dead burn Class C, and that's just trial number 8. Here's our strength results for those. And then in 28 days, we were getting 7,000 PSI. Which is pretty good. And just real quick offhand is Airfield specs, you have to have 5,000 PSI compressive strength, and then they also want a 650 flex strength at 90 days. So dead CT8 is the one that we went through. We did more in-depth testing. We did flexural strength, bond strength, modulus, shrinkage expansion, and then also freeze thaw. And then there's the citation for all of this non-proprietary MPC development work here as well. So we went through and, all right, we can make it at 1 cubic foot, and it does well. Well, we're eventually going to scale this up large, so we went through and did a scalability study, so we made it at 1 cubic foot. We made it at 4 cubic foot, and then here we actually made a half cubic yard, and because, a lot of times with concretes in general, you can really see your admixture dosages will need to change as you scale your batch. So we were curious about that, and we actually did not notice any scaling issues for our material. So large-scale trial number 1, this was in April of 2017. It is to utilize airfield damage repair techniques to enable large-scale MPC placement. So what you're going to see on the screen, I'm going to talk about it first, is a simplified volumetric mixer. So it's simplified, it being that it only has one material hopper in it. All the material that goes into it is pre-blended, and then there's a water tank on the side of it. There's a conveyor belt that pushes your material towards your auger on the back. There's also a water spigot that's feeding the water in at the same time, and all the mixing is done in the auger itself before it's discharged. And that's just a way to get you more working time with a rapid setting material. So we did this out at our test site called Poorhouse. We partnered with CTS Cement to dry blend our materials at our mix designs. And then it was a variations. We did 4 variations of that dead CT8, and we cast 8 foot by 8 foot by 8 inch thick slabs. And a big key to this was everything I had done in the lab to this point was all mass. It was all just going into a regular concrete mixer. So we also had to evaluate how that mass proportioning transition to a volumetric proportioning. And so the 4 different mixes we tried, is basically the first three are variations of dead CT8, but with different aggregates. So we used a local aggregate, we used the local to CTS aggregates, and then we used a 3/4 inch aggregate. And then MPC mix number 4, I altered the aggregate to binder ratio some. So I increased the aggregate to binder ratio. So those were the differences between the 4. And then there we are placing it, QA/QC, just normal. There's our 8-foot by 8-foot by 8-inch slab. That's us catching the sample. That's the auger right there. And then curing, we ended up sort of having to ground truth curing methods. Because I know that the phosphates can leach out of the system, but we don't want to have any drying shrinkage, we ultimately settled on a curing method that was just covering with plastic. No additional water was added to the surface of the material. So that's one thing that we sort of learned on the fly, but I would like to go back and research some more. So here's the problems, is if you can see right here, is we had pack set issues. And so we got these super sacks bulked up, and we got boulders coming out of them. And that is our guy standing on top. We're trying to break up the material. That's a sledgehammer head trying to break it up. And so that's the outcome of this placement. We went ahead and did our best, as you could see on the previous slide, but we did not get the strength results that we wanted. And so how is this pack set happening? And so, you know, this is our lab test results. This was the field test results, much lower strength, sort of a curve that doesn't make too much sense. It's not a normal curve. And then potential causes, particle packing, dry blending. The way they load the super sacks is they blow it in with the, you know, airline hose, and then, or it could be due to vibrations during shipping. And so, two main causes for clumping is physical compaction or hydration, moisture ingress, so physical or chemical. We started out with a physical process. We worked with CTS, some of their research group at the Pavement and Infrastructure group, and they went through and did pack set investigations. So that whole process is, they developed this procedure. You take your dry constituents, you blend it to a mass of 35 pounds, you put it in a sealed bag, you put the bag in a bucket, you put a weight on the bucket to simulate the 3,000 pounds of the super sack. And then you take it out after 30 to 120 days, and you see if it's pack set. If it is pack set, you put it on a vibratory sieve to see how much vibration it takes for that dry material to come apart. So that's the test. And then the parameters they changed was the pressure applied, the hygroscopicity. I probably butchered that, but it's a difficult way to say how much moisture it absorbs in these conditions, 73F, 50% humidity. And then also they looked at coarser grade materials, so like a coarser grade of mag oxide or a coarser grade of the phosphate salt. And too much animation, but they got minimal results out of it. They saw no difference after varying all those parameters. And so if it's not physical, then it's chemical. What's going on? So back to the drawing board. So now we went from a pack set investigation to a false set investigation. And so it's the same pack set testing methodology, but they started removing pieces of the binder one at a time to see what it was. And so they varied the M to P ratio, the fly ash replacement percentage, the boric acid dosage. They also tried the addition of anti-caking agents like silica or micro talc. And then results was reducing the boric acid dosage alleviated the pack set. Well, that's a problem because we need that boric acid for our set time. And so where do we go from here? And they actually came up with dextrose, another sugar. And they went through and they did a dextrose combination with the boric acid of 25% boric acid, 75% dextrose. And they did a few iterations of this, but long story short, with the dextrose boric acid combination is that they maintained performance. Pack set was no longer an issue. And then this plot over here is our strength results from those mixes. So back to ERDIC validations of, so CTS finds that boric acid was causing our issues. Send it back to us. We start working to validate it. We increased the magnesium phosphate mass ratio from 0.68 to a 0.8 as part of this change, so we altered the binder some. And then we introduced a new aggregate, rhyolitic trap rock, to improve thermal resistivity. Wasn't a whole lot of science behind it, but we just know that that is a type of aggregate recommended in the UFGS standards, and so we picked it and hoping that it worked out, and it eventually did. So the property studied, unconfined compressive strength, flexural strength, time of set, and time of set is interesting. As you can see, we eventually got to about 40 minutes for the initial set, and then it just really takes off after there. And then I got some more research I'd like to do about time of set with that thixotropic behavior I was talking about. So then we move on to our large-scale trial number 2. This was August 24th of 2021. So the similar goals is transition MPC from mass to simplified volumetric mixing, determine the mixer settings. So I talked about the conveyor belt. This controls the gate at the conveyor belt, how much dry material is coming out, and then determine the production rate. Okay, can we do a 10-foot by 10-foot slab? Can we do a 20 by 20 slab? How big of a slab can we do? Verify that the pack set solution was actually solved. Verify dextrose BA combo, evaluate the mechanical performance, constructability, and then also finishing and curing procedures once again. So these are a lot of pictures, but we did a 20 by 20 by 16-inch slab. It was a hot day, I remember that. So there's our slab, there's our mixer. There we are getting started pouring. There we are, I brought out handheld mixers to help with any potential layering. But as rapid set's going down, just more raking. I'm collecting the QC sample. There they are making flex beams and cylinders. That's just the SVM, simplified volumetric mixer, being reloaded. And then there we are getting pretty close to the top. Just some more handheld mixing, just make sure that we don't have any unintentional cold joints in the slab. So we're getting pretty close to topping off. And then there we are using a vibratory truss screed. That thing was a monster, and not in a good way. And so what we learned from it, this one didn't go well either, I'm going to be honest. So we were unable to attain the desired fresh properties. Long story short, as I mentioned earlier, that the water cement ratio for magnesium phosphates is a 0.2. Well, that simplified volumetric mixer is made for CSA-based cements, and so it's running at those run at a 0.4 thereabout. So we're getting twice the water that we needed. So the water flow is too high. The mixing auger was unable to handle the highest gate setting, so we couldn't get enough dry material into the auger to get the water cement ratio right. So therefore our strengths were not good. In fact, we went back a week later and our slab was still soft to the touch. Yes, we stubbed our toe pretty good, but I will say pay attention to this date. It gets exciting pretty quick. But one of the determinations was 20 by 20 was unfeasible. It's just too physically taxing. We had, I think if you look in that picture, that's probably 2/3 of our group that was out there, and we were worn out. So it's probably from a constructability standpoint too much. Set times were longer than observed in the lab. Well, that was because our water was too high. And then also there could be a scaling issue. So what we did to correct this is we installed a valve on the simplified volumetric mixer. That's just a valve right there. We went out there with a 5-gallon bucket and measured flow rates and figured out how many turns of this valve we needed to do to get our water cement ratio right. And we, obviously that comes along with the gate setting as well. So we measured the flow rate of the dry material coming off the mixer. Planned placement size reduced, and then we also reduced the dosage of dextrose from 3% to 2.5%, and we held the boric acid content at 1%. We were a month out from our placement at Cannon, and I will say I was nervous because we didn't have time to get more super sacks ordered and get them delivered and do another trial placement like I wanted to. But I thought I had good judgment. Luckily, some of our leadership thought I had good judgment, so they trusted me with it. I think it worked out. Yeah, and we were unable to verify before we departed in, I believe they left less than a month from that. So here was the plan, Cannon Air Force Base. We repaired 3 parking areas for V-22 aircraft at Cannon Air Force Base. So right here where this one's parked, that was A1, A2, and B1 over here. You can see the visible staining. I mean, you pull up Google Maps and you can see this staining. And so we're replacing these 3. We're going to evaluate MPC, regular concrete repairs, regular pavement repairs on either side of each aircraft. You know, you got MPC on this side, PCC on this side, theoretically same aircraft. And so you can get a real good comparison. We also wanted to look at full and partial depth MPC replacements. And then we had a big team. We had a combined team of 19 personnel, 14 from our geotechnical structures lab, 4 from our cold regions, and we had 1 guy from AFCEC out there making sure we were doing things right. And so here's the whole process: mobilization, demolition, site prep, test slab placement, repair placements, finishing, and then demobilization. You know, most of our crew, 14 of us came from Vicksburg, and we hauled all of our equipment from Vicksburg, Mississippi to Clovis, New Mexico. So we had to get everything out there and figure out how to get everything back, and rental contracts and all the like. So this is the plan some more. So for A1, you had MPC, PCC on either side. A2, we did a partial depth on one side and a full, no, I have that, yeah, partial depth and full depth on either side. And then you also had B1, which was just another PCC, MPC, but the B1, we had some guys come back at a later date and apply just some heat-resistant coatings to them to evaluate coating performance with the magnesium phosphate concretes. So mobilization, this was our yard. There's the placement site. This is the Dirt Boys house, as we like to call it. So this is our stand down to sit down every morning, every evening, deliver equipment, transport, base coordination, initial inspections, and then test placements. So first we started, so this is after I had made those adjustments, and we had, you know, a couple hundred super sacks of the material show up without any validation. But we did a test placement, so we wanted to determine the water valve position, make sure that was correct, determine the gate settings, evaluate the modified retarder dosage, obtain the desired fresh properties, determine cure time before doweling. That was a big thing. And actually, I believe in this picture, our dowel bit got stuck. So that drill bit became a dowel. And so determine cure time, and it ended up, we came back a day later, it was too soft, came back 2 days later, started drilling, had a drill bit get stuck, and then we determined that 3 days was the right amount of time. But we were unable to verify strengths, which once again made me very, very anxious. So step 1 at repair jobs, demolition. So I'm going to generally go left to right, top to bottom. But this whole left side is doing joint cutting. So there's a skid steer mounted saw, walk behind saw. We did have to, you know, it's an active airfield. We had to pay attention to the mooring points and the static ground lines and all those sorts of things. So we did mooring point relief. We did a pretty good job not damaging those. There's the excavator, full depth excavation, and then there's the partial depth excavation, which involved a lot of smaller walk-behind saws that we sort of checkerboarded and then came back with jackhammers. Everybody got a turn on the jackhammer. And then pavement removal, and then there I am stuck with a dump truck full of concrete that wasn't chipped up too small. So site prep, so you demo, you get everything out of the way. Now it's base prep. Now you got to get back to a good base. So base prep, you know, compaction. We did form work, there's dowel installation, there's dowel drilling, we're also over here, we're leveling the form work, more dowel drilling. I guess I got these pictures swapped, and then there we are putting static ground lines back in the ground. So we also went through expansion joints, tongue-tied. Mooring relief, so that's just a foam board that we wrapped around the mooring points. And then also there's our fully prepped area. It's a 10 by 10 MPC slab, dowels coming out, expansion joint material. We didn't need it on that one, but there we are getting ready for placement. So placement is we preloaded materials. There we are doing the placement. We had QA, QC here, slump tests, beams, cylinders, and the like, doing the screeding, floating and edging, broom finish, and then ultimately, instead of going with the plastic like we did in some of the initial steps, we just went with a curing compound. So after placement, we came back and cut in some control joints. As far as the MPC is concerned, a lot of the control joints were just cut where existing joints were. And so we wanted to keep that the same. There's the cutting wheel, cleaning the joints, removing debris, installing backer rod, and then installing the joint sealant. And then coatings applications occurred in November of 2021. We had a couple folks go out. Those are the different coatings they applied, and then also a silica grit mixed into it. So here's the results of Cannon. Is all specimens did get transported back from New Mexico to Mississippi for testing. Compressive results were favorable. We were generally, above our 5,000 psi threshold. However, our flexural strengths were not as high as desired. We wanted 650. We ended up around 500, 450 to 500. We did some quick calculations. The V-22 is one of the lighter aircraft, and so we figured that about 500 was tolerable. So those pavement, more data. And then, so the reduction in strength is with increase in slump. So this is kind of only measure. I didn't have a measure of the water going in. Sort of the only measure I had was the slump, because I know water increases the slump. And in general, you see a decrease in strength with increase in slump coming out of the volumetric mixer. So that was done in 2021. Went out and did the first inspection 6 months later. There's been 2 more subsequent inspections, so 3 total. So at 6 months, there was staining observed, no damage near staining, no difference between the PCC or MPC, slight scaling near the joints of the MPC, and then coating chipped on both the MPC and PCC. So here's the 2.5-year inspections, and the big story is the spalling of MPC along slab joints. So there's your MPC slab joints. This one's pretty bad here. However, the slabs were undamaged where they were stained. So it was a joint issue. It wasn't a POL issue. And so the spalling hypothesis is difficulty finishing due to rapid setting, poor consolidation of the slab edges, truss screeding. Maybe we didn't do a good enough job with the truss screed, getting it level with the existing concrete, and it could also be snowplow damage if we didn't get it leveled well enough. So conclusions is MPC can successfully be used for pavement repair applications, full or partial depth. I think we preferred the partial depth, even though there's a lot of jackhammering involved. The simplified volumetric mixer can be used for it. Partial depth repairs reduces equipment. Heat-resistant coatings did not work. Doweling and joint cutting, so basically the constructability of airfield pavements, a lot of that can carry over to MPCs, and then the joint damage needs investigation. So that rolls into our current and future work. Is current efforts, we're trying to understand what caused the joint spalling, evaluate placement and finishing procedures as part of that. I want to evaluate alternative retarders. I'm hoping to find one that doesn't degrade strength. And then I would also like to investigate the flexural strength issue some more as well. It seems like MPCs have a lower compressive to flexural strength ratio than we're used to in regular concretes. So current collaborations are going with one of Cameron's students, Riley. She's helping us develop sort of a 211 style, if you will, method for developing magnesium phosphate concretes. And then suggested research, as I alluded to, is alternative retarders, matrix alterations, strength dependence on MgO freshness. I put limestone aggregates here because early on we decided not to use limestone aggregates because I read that they could be reactive with the sodium phosphates. But we ended up using a potassium phosphate, and he used limestone aggregates throughout his whole project and didn't see any issues. So I'm curious, for the potassium phosphate, if that's even an issue, and then also the thixotropic behavior. So back on my time of set plot, just visually, I thought that if you keep it agitated, it may stay, it won't set up for a while. And so I put it in a mixer and let it sit in a mixer for an hour, and it actually stayed viscous and fluid. I mean, not viscous, it actually stayed fluid. But as soon as I took it out of the mixer, it flash set. So that's interesting behavior to me. But there's the whole team. There's all 19 of us. We spent a month of our lives out there. And that's it. Any questions?